Welcome to this video. In this video, we will discuss the properties of similar triangles. Let's quickly understand what are the similar triangles. The definition of similar triangles is that the triangles that are similar in shape irrespective of their sizes are called similar triangles. So here it mentions triangles are similar if they have the same shape, but they can be of different size. Now, before I apply this similarity property only to triangle, I would just like to state that similarity is not the concept that is constrained to only the triangles. The similar figures can be found in quadrilaterals, in circles, in 3D figures as well. So, for example, if we say that Taj Mahal and the prototype of Taj Mahal, they would be similar figure if their sides have been taken in exactly the same proportion. So, the two figures are called similar when their corresponding sides are following exactly the same proportion. So, they are still similar even if they are rotated, they are mirrored, so it doesn't matter as long as the shapes are identical and irrespective of the sizes, we call them similar triangle. For exactly the same size, there is another term coined that is called the congruent triangles. So the two figures are considered congruent if their shape as well as their size are identical, right? But congruency is not something that is very frequently used in GMAT, and congruency is anyway a subset of similarity because when the ratio of the corresponding sides becomes 1, then they are congruent. So to give you a very basic understanding of what are the congruent figures, we could say that the tiles on our floor that we see, because they are of exactly same shape as well as exactly same size, so we can call them two congruent figures. However, if we have one square tile on the floor and if we have one square tile in the bathroom, then the two tiles may not be of the same size. However, since the ratio of the sides are exactly same, so we will call them similar and not exactly congruent. So these are some examples. However, now we would like to apply this concept to the triangles because we are discussing it in triangle. So there are two cases of similar triangles that I would like to discuss. The first is the easier case. So let's start with this. I would like to draw a triangle ABC, and in this triangle I have drawn another line DE which has been drawn parallel to side BC. So as per the parallel line property, we can decipher that angle B will be same as angle D because these two will be the corresponding angles. Similarly, angle C will be same as angle E because these two will be the corresponding angles, and angle A is common to both the triangles, and as long as the angles are same, the two triangles will be similar. In our school, we study many theorems to prove that the triangles are similar: SAS, SSA, AAA. Now we are just going to discuss only one property here to prove that the two triangles are similar, and that is AAA. For any two triangles to be similar, just their angles must be same. In fact, not three angles. If exactly two angles are same between the two triangles, then third angle will eventually be same. So we are just coming down to the minimum two angles in between two triangles should be exactly same. So here B is equal to D, E is equal to C, so A is common, it has to be same in both the triangles, so the two triangles are similar. Now we write it this way, that triangle ABC will be similar to triangle ADE. The benefit of similarity is that the ratio of their corresponding sides are exactly the same. So how we take the ratio of corresponding sides are, okay, let me quickly mention what are corresponding sides because this is the term that I keep using. Then corresponding sides, we may say, are sides in the two similar figures, sides opposite to the same angle in two similar figures. For example, in triangle ABC, let's take side AB. Then AB is the side opposite to this triple marked angle. So in the smaller triangle, the side opposite to the triple line marked angle is AD. So these two sides become corresponding. Similarly, BC, which is the side of bigger triangle, is opposite to this single line marked angle. So in the smaller triangle, the side opposite to the single line marked angle is DE. So BC and DE are corresponding. And similarly, the third side is AC, and that is the side opposite to this double line marked angle in the bigger triangle. So in the smaller triangle, the side opposite to the same angle is AE. So this will be the ratio of the corresponding sides. That's one way of finding out the ratio of corresponding sides. Another way is also a fine way, but I don't endorse it much. I would only share that once. To find out the ratio of corresponding sides, the alternative strategy that some teachers in schools follow is they read the name of the triangle in the specific order, and therefore they put a cap above the name of the triangle. So when I read the name of the triangle ABC as ABC, just understand what is the direction in which I have read the name ABC. So I have read the name by taking into account, first I am reading the vertex of one line angle, then double line angle, then triple line angle. So the other triangle also should be read exactly in the same order of their angles. So in the other small triangle, the order in which I should read the name should be ADE, because I have to again follow the same order of the angles, single line, double line, triple line. So that is ADE. I don't read it AED or DEA or DEA, anything like that. It has to be read exactly in this ADE way. What happens is, in this case, you can simply take the first two letters of the first triangle name and the first two letters of the second triangle name, and these two will be the corresponding sides. For example, AB over AD is the first ratio. Then the last two letters of the first triangle and the last two letters of the second triangle, BC over DE, and the first and third letter of the first triangle AC and the first and third letter of the second triangle AE. So this also can be used to find out the ratio of the corresponding sides, but I don't endorse it because in the questions that require the use of similarity principle, we don't need to write all these three ratios. In fact, what happens is we just need to pick that which two ratios should we take and then equate them in order to get the value of the unknown or maybe an equation. So that's one thing about the similar triangles. Another very important fact about the similar triangle is the ratio of their areas. Now, let's understand how to find out the ratio of areas. If I am looking at the ratio of area of triangle ABC in the numerator and area of triangle ADE in the denominator, then for the first triangle I will have to say that the area can be represented as half of base, which is, let's assume that these are 90 degrees angle. So I'm taking the base as AB and the height as BC for the triangle ABC, and I'm assuming that angle B is equal to 90. That means angle D will also be 90 because these two are similar triangles. Then for the other triangle ADE, the base and height that I will have to take will be AD, because that becomes the base being this angle 90 degrees, and DE will be the height. Now if you see this carefully, then half cancels out each other, and AB over AD is the ratio of the corresponding sides, which is same as BC over DE. So the same ratio has come here twice. So if we say that the ratio of the corresponding sides is defined as S1 over S2, we can say that the ratio of areas can be defined as S1 over S2 square, because we have got the same ratio coming here twice. And this becomes a really important property, so we often write it in this form: A1 upon A2 of the two similar triangles is equal to S1 over S2 square. That means the square of ratio of corresponding sides. That means the ratio of areas of two squares will be the ratio of their sides and square them. So if the ratio of the sides is 1 by 2, the ratio of areas will be 1 by 4. If the ratio of the sides is 1 by 3 for two squares, the ratio of areas will be 1 over 9, right? So this is really an important property for us to know. Now, having discussed this case of similar triangles, now we would like to move to the next case, which is slightly complex, and we need to understand that because that's the most frequently used case in the questions of GMAT. Alright, so here I take them away. Now the next case that we want to discuss is the case of a right triangle. So we have a right triangle here ABC. In this right angle triangle, we have dropped the perpendicular from point B on AC, and we are calling that perpendicular as BD. Now, after having made this construction, now we come across three triangles here. What are those three triangles? When you see, we have one triangle ADB, this one triangle. The second triangle is BDE, that means BDE. So we have the second triangle coming here, and we have the third triangle ABC, which is the old bigger triangle. And all these three triangles are going to be similar. Now we are going to derive that how these three triangles are exactly similar. So let's take the angle of triangle ABC. I'm just assuming one angle to be X. Now we know that one of the angles is 90 degrees. So the third angle automatically becomes 90 minus x, because we have 180 degrees as the sum of three angles, and two of the angles we already know is 90 and x. So the third angle becomes 90 minus x. So I'm writing this 90 minus x at point C. So the three angles that we have here are x, 90, and here we have 90 minus x. That's for the bigger triangle. Now let's look at triangle ABD. In ABD triangle, you see that one of the angles is already known, that is x, and one angle we already have mentioned, that is 90 degrees. So in this case, the third angle, if we subtract the remaining two angles from 180 degrees, then it becomes again 90 minus x. So the first two triangles have been proved that they are similar because their angles are identical. Similarly, now we move to the next triangle BDE. So look at this BDE. In BDE, at point D, we already have 90 degrees here. At point C, we can see that the angle is 90 minus x, which was mentioned while taking care of triangle ABC. So the third angle will be 180 minus the remaining two angles, which are 90 plus 90 minus x. So it becomes x. So all the three triangles now have exactly the same angles. So the three triangles become similar triangle. Now we are going to exploit the advantage of similar triangles, and I'm also going to teach how to take the ratio of the corresponding sides. So suppose we want to take these two triangles in contention to take the ratio of the corresponding sides, then it's completely up to us that which triangle's side we want to write in the numerator. Let us assume that I choose to write the sides of triangle ADB in numerator, and I choose to write the corresponding sides of triangle BDE in denominator, because I want to find out the ratio of corresponding sides for these two similar triangles. Now, the first triangle has three sides, AD, DB, and AB. Now, let me quickly see that which side is corresponding to which side in the other triangle. So, the side AD is the side opposite to which angle? Let's quickly mark the angles here. AD in this triangle is the side opposite to 90 minus x. So, in the other smaller triangle, the side opposite to 90 minus x is BD. So we write AD over BD, that's the ratio of the corresponding sides, the very first one. Now let's look at the second one. So the second side is DB. DB is the side opposite to angle X in the triangle ADB. So in the second triangle, the side opposite to angle X will be DC. So we write DC in the second triangle. Now the third is the side AD. Now let's quickly see. AD is the side opposite to, okay, I have written it twice by mistake. I wanted to write here AB, I think, because the third side that is left is AB. AB is the side opposite to angle 90 degrees. So in the other triangle, the side opposite to 90 is BC. So that's how we find out the ratio of the corresponding sides in case of these two triangles, which are ADB and BDC actually, right? So the ratio of the corresponding sides can simply be identified by taking the ratio of the sides which are opposite to the same angle between the two triangles, and the ratio of areas is always equal to the square of ratio of corresponding sides that we have discussed. This is especially the important case because many times this kind of figure has been witnessed in the GMAT questions. So now next time when you see the question, then at least you will not have to prove that the three triangles are similar. We will remember that the three triangles are similar, and then we would like to make use of the property of similar triangles, that means finding the ratio of the corresponding sides, and then we'll answer the unknown asked in the question. I hope that makes sense. Thank you so much for watching this video.